key aspect in Industry 4.0. So without further ado, let's dive right in. The world of manufacturing has witnessed or experienced several industrial revolutions to this day. And as I'm sitting here speaking to you, we are experiencing the fourth industrial revolution, and hence the name Industry 4.0. If you rewind a little bit and go back to, let's say, 1700s, it's where the first industrial revolution took place. And this is the era where manufacturing was mechanized and the machines were powered by water and steam. And quite specifically, the steam engine was the driving power for this industrial revolution. And then as we go into 1800s, this is where the second industrial revolution took place, and electricity followed this specific industrial revolution. And terms like mass production, assembly lines came into the picture. But mind you, this is also an era where plenty of natural resources were available to be included in these assembly lines. And then there were abundant labor to be used on these assembly lines as well. But as time passed on, as we come into 1950s or so, this is where the labor was no longer cheap. And with the invention of silicon-based microprocessors, the electronic equipment and computers were readily available. So converting manual systems into automated systems became a possibility. And this is where the third revolution took place. And like I said before, we are currently experiencing the fourth industrial revolution, and never before as connected as we are today. So I think this newfound connectivity has given new ways and means of, has given an opportunity for the manufacturing industry to find new ways and means to optimize the manufacturing process. And in this era, the concept of smart factory was introduced, and the basic concept behind, or the basic foundation behind a smart factory is that continuous process monitoring and data collection through smart devices, smart machines, and smart systems. And by optimizing these available systems in factories via machine learning, manufacturers have been able to create what is now called as smart factory. And the reason why that there are so much interest toward this concept is because that this helps increase efficiency and also assess product quality instantly, and at the same time to analyze a product throughout the entire production process. What this means is that usually what it used to be is we make a product, and once that's been produced, we let that go through a quality test, or if that product passes through that quality test, we ship or deliver that product to the customer. But with this concept, this allows the manufacturer to identify defects real time, and at the same time, by doing that, it allows the manufacturer to take real time or corrective measures on that part, or at least stop manufacturing or stop including or spending more resources on an already defective part. So manufacturers like Harley-Davidson, a bike manufacturing company, has been able to has adapted this concept and been able to reduce their 20-day production cycle to just 6 hours. And this has given them the opportunity to reduce the cost by $200 million. And other manufacturers like GE Motors, Audi, and Siemens have also reported similar successes. And Hence, there are other manufacturers following these same footsteps. And today, the applications that I'll be talking to you would be mainly focused on this company, which is Renisho, a 3D additive manufacturing machine manufacturer. And also I've been able to work with NSG Pilkington, a glass manufacturing company. So you can see how different these processes are, but still both of these manufacturers are implementing this concept. So you can see how much important machine learning is in this day and age in manufacturing. So when it comes to machine learning, there are a few words that I first like to clarify so that we are on the same page. So even though these words used in a similar context, these words means something little, this means something a little different. So artificial intelligence. So intelligence means actually making or helping to make informed decisions and processing data to make that exact decision. So artificial intelligence help create algorithms to do exactly that, to process data so that they can make informed future decisions. And when it comes to machine learning, we go a step further and we no longer need to explicitly program the algorithm. This allows the algorithm to learn from past experiences, and hence no explicit programming is required. And when it comes to deep learning, we go another step forward, and here we no longer need to extract features. I will explain what that means. And this, we can simply input raw materials to deep learning techniques, and they will learn from the raw material, the raw data that we have included in the algorithm. And we don't need to extract features before including these data sets in the algorithm. So since an early flash of optimism in 1950s about artificial intelligence, the subsets of this artificial intelligence, machine learning and deep learning has been able to create a larger disruption. And if you go a little deeper into what classical machine learning and deep learning means and how they differ from each other, in machine learning, we speak about two specific steps, which is feature extraction and algorithm training. So in this case, it says classification, not necessarily classification. It could be any algorithm. But in deep learning, we don't have to do that feature extraction step. That's why I mentioned earlier, these neural networks, which are consisted of maybe millions of perceptrons, will learn from the data as they have been trained to do that, and will create the outputs. So it's a good thing and a bad thing sometimes, because at least in my experience, when working with industry, they are a little bit skeptical of this black box modeling, because as they have already spent so much time with these processes, they don't trust a machine to make those decisions. So as these are very much hidden and not interpretable, there's a lack of trust with deep learning. But in machine learning, it somehow seems to work with industry pretty well, because it gives certain control over what inputs to be included in these algorithms. So we have to decide, yes, deep learning is very much helpful in a case like if you're given with, like, let's say millions of pictures to learn from, I don't think you would like to be in charge of a task like that, to do the feature extraction. So if that input set is extremely large, yes, deep learning is the best way to go forward. But if the number of inputs are much smaller than that, and the manufacturer is asking for that the transparency and control over those inputs, then taking machine learning route would be the most appropriate one. So you have to decide which one to choose from. And let me explain a little bit about machine learning further. So I told you that we have to extract features before we input data to these algorithms. So what happens is that we take the raw data set, and this is being pre-processed. So this could look like feature extraction, signal processing, dimensional reduction. It depends on how the raw data looks like. And then once that's been conducted, that becomes our training set. And once this training set is ready, we can use the decided machine learning algorithm to train. We can use this data to train the chosen algorithm. And then once that's been trained, we have the model that is ready. And then the same thing happens with another data set, which we call as the test data set or validation data set. So we use that data again on the machine learning algorithm and makes the predictions. But once those predictions have been made, the human or the person who's in charge of that process should be happy with the predictions that the algorithm has made. So only if that the person is happy with those predictions, this would be a valid algorithm to be used to make those predictions. But if not, we have to go back and maybe retrain the machine learning algorithm with more data, or maybe use another different algorithm to make those predictions. So it could be a repetitive process until we reach that point where we are happy with the predictions that these algorithms have made. So speaking of machine learning, there are basic branches that we divide or categorize machine learning into, which is unsupervised learning, supervised learning, and reinforcement learning. So the main difference between unsupervised learning and supervised learning is that in unsupervised learning, we take something called unlabeled data set. And for supervised learning, we are using a labeled data set. So what this means would be more clearer to you when I explain the applications. So to give you a little bit of insight to that, what happens is that in an unsupervised learning algorithm, we don't have a specific goal to achieve. It's more like, it's way more open-ended. So let's say we are giving a set of data set, and the algorithm decides how many clusters to be identified in that data set. But in a similar application in supervised learning, in a classification algorithm, we pretty much decide which are the clusters, so we know what are the expected outcomes are. So that's the difference between supervised learning and unsupervised learning. And another technique when it comes to unsupervised learning that we talk about is dimension to reduction. So I will give you an example of this as well. This can be used for feature extraction as well. And then we go into regression, a supervised learning technique. So both classification and clustering talks about dividing into categories, but in regression, we are looking at a continuous variable rather than categories. So that's the difference there. And reinforcement learning, in reinforcement learning, we speak of something called environment. So it's very much uncharted territory, so that the algorithm learns from the actions that they have taken. So depending on how well they have been rewarded for their actions, they will learn to make better decisions in the future. So those are the three different categories that we speak of when it comes to machine learning. So before I go into the applications, let me first give you a little bit of introduction of the process itself so that I can explain how these problems can be solved using machine learning algorithms. So, like I said, I'm working with Renishaw, an additive manufacturing machine maker. So they are making machines that creates something called laser powder bed fusion builds. So this is a category under additive manufacturing. I'm sure when we hear additive manufacturing, our mind straightly goes into inkjet printing, but there are several other categories. So this is one of those categories that comes under additive manufacturing. And this is indeed a case where we use to create metal additive manufacturing parts. This is very much important because that this can be used to create metal parts. These parts can be used in real world applications, such as a spare part in an aeroplane or even as a biomedical implant. So the quality of these parts are very critical. And that's why as we go forward, you will realize how well we should be able to certify these parts and how critical that is for this process. And the process itself is it involves three basic steps. The first one is that the powder will be deposited on this layer, on this build platform, and then a laser beam controlled by several moving mirrors. So this is a little bit complicated than this, but for illustration purpose, I'm just showing the most important parts. So controlled by several moving mirrors, we'll create a shape on the powder bed. So I will show you how that goes. So something like this happens. And as this part is being fabricated, there'll be light reflecting from these melt pools, and that will be captured back in using several photodiodes. Again, I couldn't show you the exact diagram as it makes it a little bit complicated. But as we make the part, we are able to capture the photodiode sensor measurements, and we are capturing it considering several wavelengths. So we have 3 photodiode sensors that captures the light emitted by the melt pool. And once that's being done, the build platform goes down and another layer will be deposited on top of this layer. And these 3 steps will be repeated until the entire build is being fabricated. And the defects that can be found in LPBF builds can be of many types, but specifically, so porosity, bowling, residual stresses, geometrical defects are the most popular types, but porosity is the most detrimental type, and hence the applications that I'm going to present to you today will look into porosity rather than other defect types. And usually what happens after creating these builds is that we test their quality using both non-destructive and destructive tests. And for destructive tests, actually, we cannot use the real part, obviously, because as we are destructing the part. So what we are doing is that we create something called witness specimens, so that they will have the same process conditions and the material fed into real parts. And once the fabrication was finished, we will test these witness specimens for its quality. But a slight problem with that is that even though that we believe these parts to have similar quality, it is possible that these as these are positioned different to the real parts, that they might not have the same qualities that we expect in our real parts. And when it comes to non-destructive tests, there are several techniques to quantify a part's quality. One is taking global density measurements, and the other one is taking CT scan measurements. And when taking global density measurements, we cannot exactly identify the particular position of that defect, but when it comes to CT scan measurements, this allows us to locate the exact position of that defect as well. But again, in CT scan when taking CT scan measurements, in order to have the required resolution, we need to have a certain part size. So if the part grow larger, then it becomes difficult for us to use CT scans to identify these defects. So let's go back to machine learning. So I did mention that if we are using machine learning, we have to first do the feature extraction of pre-processing of the data. And so it doesn't always have to be of someone sitting down and manually choosing all the input features or features that are going to be included in the algorithm. This can be as simple as a dimensional reduction technique as well. So this is what we are going to do here. So we first need the matrix to be formed. So with this original matrix, we can then decompose this matrix into 3 separate matrices. So here we have something called basis vectors, and here we have something called singular values. So with this approach, as you can see in these images, if we use all the 499 singular values, then we can represent the exact image. But even though we are not using all the singular values in here, we are just using 5 singular values and recreating the image, but still we are able to have most of the information in the original image. So you can see how much important this kind of technique could be when it comes to dimension to reduction, as most of the time the raw data is extremely huge, but not all the data carries important information. Only a part of it would be important for the algorithm. So how do we use this in the application or in the problem that I've discussed? So let's imagine that we have created 25 tensile bars. So this is how a 2D image looks like. So the data collected on each layer looks like this for each bar, that is. And we are simply downsampling this data set. So we are only collecting the data collected on every 10th layer. And then by separating that into different bars or different specimens, we were able to create this this matrix that is ready for feature extraction. And even though that I said that we are going to use singular value decomposition, this is a much larger data set. So we've used something slightly different called randomized singular value decomposition, but I wouldn't go into the details of it as it might complicate things. So I would mention that this is very much similar to the basic or the principal algorithm that I've discussed, which is singular value decomposition. So it's still decomposing the original matrix into 3 different matrices. So by using these singular values and basis vectors, we can recreate the original matrix. So we can express the original matrix as a linear combination of basis vectors and constants. And with that same principle, we were able to recreate our original signal. So here we are recreating using just one basis vector or one singular value. And here we are using 20 basis vectors. And as you can see, we are pretty much there with our signal with 20 basis vectors. But still, even with one singular value, we were able to recreate or at least capture the trend that we were experiencing in the signal. So using that first basis vector, the first singular value, we were able to capture the first feature. And as I mentioned, there are several photodiodes. So by using another photodiode sensor, the data collected on different photodiode sensor, we were able to capture the second feature. So we can add more features to this feature space. It's not restricted to 2 space, but I will, for simplicity, I will explain how it can be done using a 2D feature space. And so once we have the feature space ready, and we can then go on to conduct the algorithm that we are using. In this case, we are trying to identify whether parts are defective or not. So we are using its clustering or classification. So so the difference is whether we decide to label it or not. So here, if you're taking clustering approach, then that means that we don't know the label or the outcome. So we are simply inputting all the data, and with the initialization provided to these Gaussian mixtures, which is the algorithm that we are using, Gaussian mixture model with expectation maximization. So with that, we were able, in the next iteration, using something called expectation, we are able to identify which Gaussian is creating or responsible of creating these data points in the feature space. So depending that, we decide the labels of these data points. And with those decided labels, we can then recalculate or maximize these algorithms or these Gaussians for their mean, covariance, and the mixture. So I wouldn't again go into details of mathematics that as it could bore you, but these are the main parameters that we are trying to maximize. But I will say that it's very important to know that in this kind of application, when we are maximizing, there could be several local maximums. So it's very important to reach the global maximum. In this case, there are only 2, so this is the global maximum. So in order to do that, we might need to we might need several initialization to make sure that we are reaching the global maximum in this case. And the approach that we've used is a semi-supervised one. So it's both clustering and classification. So it's a collection of labeled and unlabeled data set. The reason why we are using that is because in additive manufacturing, it's sometimes very expensive to label them. So in this case, we are deciding whether the ultimate, we are testing their ultimate tensile strength. And if they are higher than a certain threshold, we are deciding, okay, that is acceptable. So it's not it's a non-defective or acceptable part. But if it's less than that threshold, it is a defective part. So that's how we categorize those parts. And with that, and with the usage of a semi-supervised approach, we were able to classify those parts with quite successfully with a 77% success rate. And Then if we go on to a little bit different algorithm approach, let's go into regression. As I mentioned before, previously it was just categories, but here we can decide we can predict a continuous variable. So the most simplistic approach is what we call as linear regression. And even in deep learning perceptrons, the basic perceptron use this algorithm and added a nonlinearity to it using the activation function. But so what happens here is that we decide the inputs, which is being applied to the algorithm, and then it will decide the θ1, θ2, and θn, depending on our input and output combinations. And then we are able to predict, given the new data set, the output for that particular input data set. But the problem with this kind of a linear regression approach is that we have to decide the order of this input data. So at this representation, I'm just using first order inputs, but it can be second order, third order, or a mixture of those components. So we cannot explicitly program it to find it. So as it is more tedious, we are using Gaussian process regression so that we don't have to. So it's called parametric modeling, and this is non-parametric modeling. So we don't have to bother about the basics function. We simply can use the data to decide that. So with that, we are using a kernel function. And the important thing here is that as this allows us to use dual representation. What that means is that with dual representation, we are not only considering about, so what happens usually is that we train an algorithm and then we use those parameters forward and test the algorithm with another data set. But with this approach, this allows us to include both testing and training in the testing stage. So this is in that way much sophisticated, or can manage much larger data set to find the best parameters for that algorithm. And how do we use it? So here we are predicting density. So as you can see, the model so the density is a function of the input features that we have chosen plus a noise model. Why a noise model? Because then it's easier for us to decide how uncertain these predictions are. As you can see here, as we have more data, we are more confident about these predictions. But when it comes to this region, as we don't have much data to rely upon, the range or the uncertainty becomes higher, and it says that we are not sure in these predictions. We are not that confident about these predictions as we were in this region. And we can include more features. So I've included just one feature in this case because it's easier to represent, but we can include more features to make the algorithm a better one. And as we go into another application, here again, we are using GP regression, but here we are using that to predict the grayscale value. So I've told you before that in the previous application, we were looking at global ultimate tensile strength, or ultimate tensile strength, and global density parameter, so which are looking at the global quality, but not specifically about, it doesn't give you details about how it looks locally. So CT scan measurements does give that, and that's why we are using CT scan measurement to predict those local details, and using that images captured from CT images, we can train the algorithm and predict using the photodiode sensors and predict grayscales using photodiode sensors. So we can include several layers, like I said. If you're not happy with the results, which were the case for us using just single layered data set. So as by increasing it to include both defective layers and non-defective layers, we were able to train the algorithm better and then predict it on a defective layer. So this is how the original image, a filtered original image looks like. And then this is how a predicted image looks like. So as you can see, it's very much close, except for these little dots are not, it's not appearing in the original image, but we do have it in here. So we have those successful predictions for those images. And sometimes we don't always have inputs to be fed into the system. And sometimes we don't have an explicit relationship between those inputs and outputs. So as we are going deeper, as you can see this time, the regions that we are looking at is much smaller and very much irregular. So it's very difficult to obtain an explicit relationship between photodiode sensors and the images. So what we then went ahead and did was we used the history of the sensor data, which is the photodiode sensor data. And using that, we were able to predict into the future, because using autoregressive models, we can do that. It allows us to use the history of the data and predict the future values. And again, we are including a noise model here as well. So if we try to predict, so we call these lines as hatch lines. It's a term used in LPBF manufacturing. So on a non-defective line and a defective hatch line, you can see that these are the predictions made using those, using that explained model. And by calculating how much accurate these predictions are, we were able to capture the defective areas quite successfully. And as you can see, these are the success rates that we have been able to achieve. And the wording, the true positive rate and true negative rate, is something also that we always use in machine learning. What is meant by that is that true positive means, in this particular case, the regions that are truly defective. So how well the algorithm is able to identify truly defective regions, which is 88.43%. And true negative means the regions that are truly non-defective. So how well the algorithm is also able to identify those non-defective regions is being expressed in the second successive rate. And these are the applications that you can use to solve a problem. And I think that this would give you a brief explanation about how these algorithms can be used in order to solve real world problems. And thank you for listening. And if you have any questions, I'm very much happy to answer them.
Thank you very much, Sarini, for your excellent presentation with all the necessary details in a very simple manner. So your presentation, I think, might have raised many questions from the audience. So let's ask from the audience if there are any questions they can ask. Now it's time. So any questions you can pose to Sarini. sorry, there until others come up with the questions. So there's one already posted by Dr. Prasanna. So his question is, how far you have covered in the area of machine learning when you at Peradeniya? Or how you switch to this area after you follow our program? Because I know the depth we cover in this area. So therefore you can tell us exactly how you adapted to this area, because it's a bit new to us as manufacturing engineer, right?
Yeah, I think the experience in the undergraduate level was that you always go into deeper level and look at how it works rather than looking at outside and applying or changing model parameters. So I think that basic rule of let's dive in and see what's happening in there, it's very much what helped me to learn a lot about these techniques. But I would say, even though it wasn't taught exactly like that, the algorithms or the coding, but I think the basic learning was there to adapt to that certain conditions that I've been that I have to adjust myself to. Does that answer your question?
Yeah, exactly, Sarini here. Very much glad to hear that answer. Thanks.
Okay.
Okay, any other questions? Okay, if there are no questions, then I'll ask one, because now this is, I know that it's kind of a new domain where most of the engineering disciplines currently rely on, especially for high-end research on machine learning side, mainly to come up with better predictions and come up with smart systems. So since you are, reasonably aware of what we teach at the bachelor's level under manufacturing engineering program, so what do you think now how we can introduce these areas even at the level of bachelor's? So do you think it's very useful, or do you think it will be right thing to do by taking into account the future trends of manufacturing?
Oh, definitely, yes. I think it's very much like you said, exactly the new trend. So every manufacturing industry is looking to convert into, like I said, smart factories. So I think it would be very much beneficial. Even though in Sri Lanka, I don't know, but it will catch up to that speed, I think, eventually. So I don't think that would be unnecessary chapter at all if we can include models or teaching modules that teach machine learning algorithms. I think that would be something very useful for everyone.
Okay, thank you. Actually, now we are in the process of revising our curricula undergraduate one. So they are actually, we have about 4 substreams. One of them is manufacturing automation side, where we try to introduce more from computer engineering side, mainly from machine learning, programming, and data structures in RPA, yeah, things like that. So at the moment, we are trying to slowly introduce these areas to some of the substreams of the main program, so that we hope in time to come these things are merged very much into manufacturing and industrial engineering curricula.
Yeah, I actually saw if it is still the one that you're talking about, the curriculum change, I saw that something called artificial intelligence from computer science department is a module that would be taught under that new curriculum. I think that would be quite helpful. I think if it is only provided to automation students, manufacturing automation students, it would be at least to give the basic concepts. If we can if it is possible, I'm just suggesting, if it is possible to include something like it doesn't have to be, because in computer science it's very much I would suspect that it would be very much deep learning techniques, which is not always the case. So then IoT, and like if you can look at the big spectrum of Industry 4.0, the IoT, big data analytics, and machine learning, yeah, if that can be taught under a different module for everyone, I think that would be useful.
Yeah, definitely. We'll keep those as some of the electives, and especially for manufacturing automation, they had to do it. Even for manufacturing engineering substream, yeah, they can take that depend on the interest, etc. Thank you for your suggestion. Any questions? Any more?
Hello.
Yeah. Please go ahead.
I am actually new to this field, machine learning field. I started deep learning specialization course in Coursera and advanced machine learning course from HSC University in the Coursera. When doing challenges in Kaggle, I got barriers with the things I learned from the courses. I still haven't completed them. Are there any resources that I can follow, and how can I make my own project using machine learning? Any advices I can get?
Yes. So I would suggest there's I don't exactly remember the course, but YouTube is a very good place to start, because there's an MIT lecturer who's doing both deep learning, neural networks, and reinforcement learning. I found that there are like 7 to 8 lectures that you can follow on that course. So I think that would be very useful. I think speaking of in a general manner, I don't know exactly the application that you're trying to implement, but if it is particularly deep learning and CNN and that kind of stuff, then that would be very useful, I think. Apart from that, books, I would suggest there's something called Pattern Recognition by Bishop. If it is helpful, I will send you those details later.
Okay, thank you.
As well. Yeah, those are the references that I would probably go for.
Thank you.
Okay, so if you do not have any other questions, maybe we can wind up the session. So on behalf of DMIE, I would like to share a token of appreciation with you. So we have a kind of a digital certificate to be offered. So I'll share that one and I'll email that to you later on. So thank you very much, Sarini, for your excellent session. I hope many of us got a lot of information from your research. So we are very happy and very proud to see your achievements, and we hope that you will successfully complete the PhD program and help us in time to come. So thank you very much. Please accept our digital certification. I'll share this through the message.
Yeah, thank you so much for inviting, and again, I didn't expect to be certified, but yeah, thank you so much for all your efforts.
Okay,
yeah.
Now I'll invite Mr. Namal Bandaranaike to give the vote of thanks.
Okay, Sarini, thank you very much for a very well delivered presentation on a very timely topic that where the industry is moving. I think you have inspired a lot of students here in the leading edge of research in a leading university. You have shown what university students graduating from the department, from the faculty can do in their future. So I think that inspired a lot of students, and hopefully the students will also take the inspiration and the possibilities that are open for them and take it forward. And your presentation also was very detailed, and it provided a lot of insights where things are moving and how mathematics and the analytical approaches that students are exposed to, how they are important in the future as well. So you delivered the third of the webinar series in 2021. We had a series of lectures back in 2020 also. So thank you very much for helping to continue the webinar series forward in 2021 as well. I would also like to thank everyone else who helped to arrange the webinar, including preparation of the flyers, the certifications and things as so hopefully we'll hear more on this webinar series going forward. Thank you very much, everyone, for your participation. We'll look forward to seeing you in the future events as well. Thank you very much.
Yeah. Thank you very much, Namal, and thank you very much, Sarini, again for your time and dedication to enlighten us on these new directions. Thank you very much, and have a pleasant day to everybody. Thank you.
Thank you.